Okay, question 7 picks up nicely from number 6. Says each graph below is the graph of the polar radius r on the vertical axis versus the polar angle theta on the horizontal axis. Use each graph to sketch the corresponding polar curve. Okay, and looking at part A, we see that the polar radius r depends on the rotation angle theta linearly. Okay, so this translates to the following in the xy plane. Okay, so as you increase theta, so in other words, as you rotate counterclockwise in the xy plane, your radial distance r from the origin grows linearly. Okay, so to sketch the corresponding polar curve in the xy plane, well, note that when theta is 0, r is 0, so that puts us at the origin. And now as we rotate counterclockwise, our radial distance from the origin has to increase in a linear fashion, right? It has to increase at a constant rate. So another way to say that, right, is that the height on this blue line in the r theta plane, which you see here in green, that tells us the radial distance from the origin over here in the xy plane, right? So here's some sample points on our polar curve. And so now if I go ahead and draw a nice continuous curve through those points, I get this spiral curve in the xy plane. This is known as an Archimedean spiral. Okay, so now let's go ahead and look at that in Desmos. Okay, as you can see, here's your green Archimedean spiral, and here in blue is our relationship between the polar radius r and theta. So as we increase the rotation angle, okay, we can see that the height on the blue line is describing this radial distance from the origin, right, out to this point on our green polar curve. Okay, and so there you go. Very nice. All right, that does it for part A. Let's go ahead and check out part B next. So for B, the relationship between r and theta here is described by a sine wave. Okay, so notice the amplitude here is 1, and we complete a full period in pi units. So this is actually given by r equals sine of 2 theta, which we don't technically really need to sketch the corresponding polar curve, but nonetheless, okay, sine wave. And notice I've color-coded it here for reasons that I'll highlight here in just a moment. Okay, so now let's go ahead and break things down in the xy plane. Okay, so first off, notice on the interval from 0 to pi over 2, right? Well, as we let theta vary from 0 to pi over 2, over here in the xy plane, we're rotating through the first quadrant. And what happens to our distance from the origin as we rotate? Well, r is going to start at 0, so we're going to be at the origin. Then we're going to increase our radial distance out to a maximum value of 1 when theta is pi over 4. So in other words, we're going to hit our maximum distance from the origin along this ray at pi over 4. And then we're going to decrease our radial distance in a symmetric fashion as we rotate from pi over 4 to pi over 2. So we're going to come back in towards the origin. Okay, so that's going to give us this little petal here in the first quadrant. Okay, so now on the interval from pi over 2 to pi, okay, well, we're rotating through the second quadrant, but this is where we have to be careful, right? Notice that r here is negative. And as we've discussed, right, for negative values of r, okay, we have to reflect points that would normally be up here in quadrant 2 if r were positive. We have to reflect those points through the origin, so that actually the corresponding points we get on the interval from pi over 2 to pi are going to be down here in quadrant 4. And again, that's because r is negative. So what's happening? Well, r decreases down to a value of -1, and then it goes back up to 0. Okay, so we're rotating through the second quadrant, and because r is negative, we're reflecting through the origin, so we're going to get another one of these petals, but it's going to be down here now in quadrant 4. Okay, so that's that portion. And then moving on from pi to 3 pi over 2, All right, well, we're sweeping through quadrant 3, and R is positive, so that's going to give us another one of these petals, and it's going to live down in quadrant 3 because, well, R is positive on this interval from pi to 3 pi over 2. Okay, and then that leaves us with this last bit as we sweep from 3 pi over 2 to 2 pi. So we're sweeping through quadrant 4, but again, R here is negative, so we're going to reflect through the origin, and that's going to give us a petal up here in quadrant 2. So we get that, this nice 4-petaled curve. Okay, so checking that out on Desmos, what's that going to look like? Well, have our polar curve here, and I've color-coded it in the same way, and then I have the corresponding curve in the r theta plane here. Okay, so as I increase the rotation angle from 0 to pi over 2, okay, you can see, right, the radial distance increases up to a maximum of 1 and then decreases down to 0 in the r theta plane. So that corresponds over here in the xy plane, right, to sweeping out this petal in green in the first quadrant. Okay, so then as we let theta vary from pi over 2 to pi, okay, our rotation is happening right through the second quadrant, but again, since r is negative, those corresponding points get reflected through the origin, and we're looking at this purple petal. Okay, and then from pi to 3 pi over 2, r is positive, and since we're rotating through, right, quadrant 3 and r is positive, then the points on the polar curve are in quadrant 3. Okay, and then lastly, from 3 pi over 2 to 2 pi, okay, we're sweeping through quadrant 4, and since r is negative, those points get reflected through the origin, and so we get this red petal in quadrant 2. Okay, so pretty nice curve there. See it once more just in action. And there we go. Cool. All right, so then moving on to the last part. This is part C. Okay, so this also happens to be a sinusoidal wave. This is a cosine wave. Again, the particular equation isn't so important here, but what we can see from this graph is that as we increase theta, okay, our radial distance, it decreases from a maximum value of 4 down to 0 when theta is pi, and then it increases back up to a maximum value of 4 when theta is 2 pi. Okay, so let's go ahead and get a feel for what we're going to see over here in the xy plane. So when theta is 0, so in other words, when we're along the positive x-axis, our radial distance is 4. So that's going to give us a point 4 units away from the origin on the positive x-axis. Okay, now as we rotate counterclockwise, we can see our radial distance is going to shrink at pi over 2. So when we're on the positive y-axis, our distance has shrunk down to a distance of 2. Okay, so we're starting with a distance of 4, then we're going to shrink that distance down to 2, and then we're going to continue to shrink that radial distance down to 0 as we rotate from pi over 2 down to pi. Okay, so we're going to sort of spiral in towards the origin. And then from pi to 2 pi, we're basically going to just undo what we just did, right? So we're going to spiral out back to that starting point. So here are some key points on our polar curve in blue. So we're going to spiral in and then spiral back out. Okay, so this is another one of those heart-shaped curves on its side. This is known as a cardioid. And again, the height on this red curve in the r theta plane, that's describing our radial distance from the origin, right? So that distance starts out at a max at 4, and then it decreases down to 0 when theta is pi, and then it unwinds, okay? So here is that same curve here. As we rotate, okay, again, this height on the green curve is telling us this radial distance from the origin out to our point on the blue polar curve. At pi, we see that distance shrinks to 0, and then we just unwind. Okay. Well, that's going to do it. I'll see you in the next video. Thank you.